Welcome. This is the second video about the Huntington-Hill method of apportionment, and we're still on page 5 of the notes. So in the previous video, we discussed the rounding rule that's necessary for the Huntington-Hill method, and in this video, we're going to actually do an example. So we have 6 states and 200 seats to apportion. The states' populations are given in this table. And for instance, you can see something like state B is not quite as large as 2 times the size of state C. So in the apportionment, state B should get not quite as many as twice as many seats as C. Because proportionally, that's how it would be. And the apportionment methods all try to match proportional the proportional distribution as best as they can. So in all of these problems, one thing we need to know is how many people we have in total. And so the total population is given in these in the first column of those tables below. So there's a couple tables here. We're just going to focus on the first one for now. And the total population is given here in the bottom. So if you add up all the individual populations of the state, you get 2 million. The seats available are 200,000, and you should just, check for yourself that 2 million divided by 200 is 10,000. So the standard divisor is 10,000. So if we could divide all the populations exactly by 10,000, then these quotas would be how many seats each state should get. And you can check that 344,970 divided by 10,000 is 34.497. That's just moving the decimal place over 4 times. And all of these numbers in the quota column are the population divided by the divisor. That's the starting point for all of our methods. Now, the Huntington-Hill method says that the way we will round these quotas to whole numbers is based off the geometric mean. So what this cutoff is right here, this cutoff is the square root of 34 times 35. And the reason why we're looking at 34 and 35 is because we're having a question, how do we round the number 34.4970? Should we round it up or down? With conventional rounding, that would obviously go down because this is less than 0.5. But with the Huntington-Hill method, the rounding cutoff point is not 0.5. It's the square root of the 2 whole numbers nearest to the number that you're trying to round. So we see that the cutoff point is 34.4964, and 34.4970 is larger than that cutoff point. So you see that this number is rounded to 35. Now similarly, all of these quotas are rounded based off of these cutoff points. And as whole numbers after that rounding, this is the list. So this would be your apportionment. But your apportionment gave out 202 seats, and you only had 200 seats to give out. So we have to search for a different divisor. That's the way these methods work. If the first divisor doesn't work, you search for another one. And changing this divisor will change all of these quotas, which will of course change all of the roundings. So because we apportioned too many seats, that means our divisor should increase. Because if more people are to be represented by any individual person in the government, then we'll need to apportion fewer seats. And so if we're trying to decrease 202, we'll increase the divisor. So that's what the second table does. And the second table has one extra column just to remind us what the standard divisor was. So you can see that this column in yellow is identical to this column in the first table. So we can highlight that point. Now in the second table, we've chosen 10,100, and choosing the divisor is a guess and check. Now, there's educated guesses and checks. You don't want to go and change the divisor to 20,000. That's a little bit too far. We're pretty close to apportioning the correct amount of seats, so we don't need to go and changing this divisor too large. You don't change the seats available, and the populations of the states don't change. This divisor, divided into each of these populations, gives these quotas. And you can check that the number 34.1554 is smaller than its corresponding number in the previous table, 34.4970. It makes sense that this number is smaller because you're dividing by a larger number. When you divide a number by a larger number, you get a smaller number. Now, we use the same cutoff points talked about in the previous table, and when we do the rounding, we've apportioned 197 seats. So when the divisor is 10,100, we don't apportion enough seats. This number is too large. So now we have to back off. And we should choose something between 10,100 and 10,000. Because 10,000 apportioned too many seats. 10,100 didn't apportion enough. So now you're in a round of guess and check. And I'll save you the guessing and the checking, but a divisor that works is 10,001, so just one larger than the standard divisor. And what happens? All of these numbers get divided by 10,001 and produce these numbers in the quotas. Using the Huntington-Hill cutoff point rounding rule, we get these numbers, which add all up to 200. You can see the difference between the original Huntington-Hill rounding and this result from having a divisor of 10,001 is that 2 fewer seats are apportioned, which is exactly what we needed to happen. So the seats apportioned now match the seats available. And the difference is this is a 34 instead of it being a 35 in the original one. We can draw arrows to that. And also, it looks like this 15 is where the other change came from. So that is the Huntington-Hill method. It's just using these. It's still all about picking the appropriate divisor, and the difference between this method and and Jefferson's, Adams, and Webster's method is just the rounding rule. Let's take one moment to look back at the standard divisors. So when we divided all of the populations by the standard divisor, we get these numbers. And just to make a note, if we had used standard rounding rules, then this number would have been 34, this would have been 41, this would have been 22, this would have been 59, this would have been 15, and this would have been 29. And notice that this list here matches the same apportionment from the Huntington-Hill, where the divisor was 10,001. So the Huntington-Hill method and the Webster's method would have produced the same result would have produced the same apportionment, and Webster's, which uses the conventional rounding, would have also just given that result immediately with the standard divisor. So that's just a comment to note that sometimes these different apportionment methods give you the same result. Alright, that's the last of the methods. In the next video, we'll discuss some of the paradoxes and issues with these apportionment methods. See you there.